All right, so today we're going to go into doing distribution. All right, so we're going to start with mean, median, mode, standard deviation. We've seen these before. You saw these last year, but we're going to just go over this again today. Real quickly, mean, the average of the data. Symbolically, you'll see this as U or U prime. And when you see that, right, U or X bar, sorry, it's the sum of all numbers over the total number. So basically, guys, it's your average. You guys know what that mean is. It's your average. Median, we put the numbers in numerical order, and it's the exact middle number. Now, you can find which number in order is your median by doing this n plus 1 over 2. So like if you had like 7 data points, if you add 1 to it, that's 8 divided by 2. The fourth number in order would be your median. So like if n again was 7, so we go 7 plus 1 divided by 2 would be 8 divided by 2, which would be 4. The fourth number in order would be that. So let's just say you had 1 through 7, number 4 would be your median. If you end up with an even number, you have to take the average. So it'll be your average of the fourth and fifth number. So let's just say you had 8, right? 8 terms. Let's say n was 8. 8 plus 1 over 2, that's 9 over 2, which is 4.5. So it would be the average of 4 and 5, whichever the fourth and fifth term are. That would be your median. So again, that's just a way of finding it. The calculator will do this for us if you do not remember. Mode, most frequent number that occurs most. Range, whatever your max minus your min is. Again, you've seen these. Now, things you do need to take care of. Standard deviation, that is one you need to know. It is represented by this. This is what is called lowercase sigma. That's what this little O with a hat on it is. So do not worry about it. Or S. Most of the time, we're going to just deal with the sigma one because we're going to assume that that's all population. And if you take statistics, you'll get more into this. And basically, what standard deviation represents is the average how far a data point is away from the mean. All right. So if you think about it, you have a bunch of data. We find a average for that data or a line, and the standard deviation tells us how, on average, how far each data point is. It's not exactly what they will be, but how far away on average it is. And what we have here is we call the variance. Now the variance is basically your standard deviation squared. So you see it's just sigma squared or S squared. So it's the square and spread out. The data is from the mean, and here is your equation. If you actually read this or learn to read it later on, it is the sum of your average minus every term squared divided by n. So basically it's an average of the spread. So again, we're not going to make you guys do this. Calculator will do a lot of this for you. All right. Now, if you do not remember how to do this on your calculator, I'm going to give you a quick synopsis here on how to do it. So we're looking at our calculator. Remember, we want to be able to put data into our calculator. So to do that, you should remember this from doing linear regression last year and stuff like that. First button we hit is the stat button. It brings up our list. We're going to go into edit. And you see right here, I actually have some data already in there. I'm just going to clear it out. So if I'm actually having to do numbers, this is what you do. And you would put in numbers. And I'm just going to put in a few random numbers. All right. 9 of them's good. All right. And then what you're going to do is to get these numbers, our mean, median, standard deviation, all that. What we're going to do is we're going to go back and hit our stat button, and then we're going to go over to calc, and you'll see that the very first one in the list is one variable statistic. So when we only have one data set, and we're not comparing it between two, we use one variable statistic. You guys would use number 4, linear regression. Now, that's fine and dandy, and that actually gives you, an equation. But we want one variable statistics. If we do that, we hit enter, and it should bring up this list. L1 is what we put our list in. We're not going to touch frequency list, and you just hit calculate at that point. And you'll see you get all these numbers. And you see the very top one, it says X bar. Well, if you realize X bar is our mean, that's the mean of all the numbers I just plugged in. So 5.89, that's what I would count as my mean. So that's my X bar. And then you see we have this sigma x and x squared. We're not going to care about that. And then you have this sx and look, there's our little buddy there, the sigma, or the little O with the hat on it. Sigma x. That's my standard deviation right there, and that's what we would use. So, I mean, right off the bat, we have this one as our mean, and then we have this one here as our standard deviation. You'll see me rewrite standard deviation a lot as SD. It's the easy way. So my standard deviation here is 1.97. So on average, all my data points are about 1.97 away from 5.89. All right. And if you look lower on this, right, even lower on the calculator, you'll see that we get a bunch of other things. That n is the number of data points I have, which is 9. We did that beforehand. And then look, you got a min, Q1, median, Q3, max. Well, guys, there's my min and my max. It's 9 and 2. And there's my median, number 6. And hopefully you remember last year from Q1 and Q3, where they came in to be part of that 5-number summary. Now, we're going to not do it box and whiskers today, but if you happen to do it, you'll need this. That's your 5-number summary on the bottom. But we like mean, we like the median. You know, the one thing the calculator won't do is do your mode. That's something you have to figure out yourself. It can sort it, but I'm not really going to get into that today. All right, so back to the notes. So that's just a quick synopsis. If you need more queuing on that, you know, pause it, rewind it, and do this. All right, so we're getting into what was called normal distribution. Now, when you get large amounts of data, what you tend to end up with is you tend to have the data forms what are these normal curves. It's just really weird, but for the most part they do. And if you think about it, guys, the best way to do it is like your height and weight. As kids, they do this normal curve. The middle would be the median, the average for a certain person at that age or how they grow. And then, you know, to the right and left are your higher and lower bounds. Depending on how the data is or how much data is, you can get things like this one on the left, which is more of a standard normal versus the one on the right here, which is a very compact normal, but it's still normal. The mean is still the middle. All right. So normal distribution is probability distribution. So it calculates probability and associates the normal random variable x with a cumulative probability. All normal distributions look symmetric, bell-shaped curves. So we also call them the bell shape. And the reason they're bell-shaped is they look like a bell. Now, what you'll see is that also it says cumulative probability, which means, guys, this all the area or numbers underneath it will add up to 100%. So we can add the probability up as we go along. We'll get into that here in a minute. The graph of the normal distribution depends on 2 factors, the mean and the standard deviation. Now, everything is based on mean and standard deviation. None of this has to do with the median, max, min, whatever, just the mean and standard deviation. All right. The mean of the distribution determines the location of the center of the graph. So every time we look at it, my mean is my dead center. So no matter which one we're dealing with, that is my mean or my x bar or mu for that case, just depending on how we're going to call it. Most of the time we're going to try to use mu, but it doesn't matter. And the standard deviation will help determine the height of the graph. So the bigger the standard deviation, the flatter and wider it gets. So this would have, the first one has a bigger standard deviation than the second one. The second one has a very small one, so everything's compact. It's not spread out. Again, because standard deviation measures spread, bigger the standard deviation, the more spread out our curve is. The smaller, the more compact. So when this deviation is large, the curve is short and wide. Again, when it's small, it's tall and narrow, as you see up here. So we see bigger on the left, smaller on the right. So let's just be able to read normal distributions. Do not worry too much about copying all this down, but you do just need that bottom part. Now, here's a standard normal. This is a standard normal curve. This is what we call a standard normal curve. All right. And the reason it's called standard normal is because the mean is 0. Means on average you're 0. And you'll see that we have these markings, 1, 2, 3 to the right, -1, -2, -3 to the left, just like a normal number line. Well, these are my standard deviation. That's 1 standard deviation to the right, 2 standard deviations, -1 standard deviation to the left, 2 standard deviations to the left. So all these are standard deviations, and what they do is they will segment the curve into different portions, and we'll get into what they mean here in a minute. But what they do is we can do this. And so every time we set up a normal curve, guys, your middle number is your mean. So here is my mu, or my x bar, however we want to represent it. And to the left, we'll do usually 3 standard deviations. To the right, we'll do 3 as well. So this is our standard normal. Get used to seeing this. We're going to deal with this a lot. All right, so here's something we're going to get. You're going to get something like this. You're going to label the normal distribution with a mean of 20, mu, 20, and a standard deviation of 4. Make sure we label 3 standard deviations. So what I'm going to do is, knowing my mean is 20, I'm going to automatically, and I'm just going to draw a straight line straight down from the top. You don't have to, but I would prefer you do it. And I'm going to put my mean as 20. I'm just going to put 20 right there. And then it says I have a standard deviation of 4. And we're going to go plus and minus 3. So we're going to go 3 to the right, 3 to the left. So what I'm going to do is I'm just going to go 1, 2, 3, and 1, 2, 3. And just kind of make them evenly spaced as best as possible. And so since we're doing 4 is my standard deviation, that means since my mean is 20, going to the right, we add 4, just like we do on a number line. 24, do another 4 for the next one, 28, and the next one, 32. Going to the left, we subtract 4. So this should be 16, 12, and 8. And there is my normal distribution set up with my mean of 20 and a standard deviation of 4. Because you know we have 1 standard deviation to the right, 2 standard deviations, 3 standard deviations, 1 standard deviation left, 2 standard deviations left, 3 standard deviations left. And don't get confused by the negatives. That doesn't mean negative numbers. It just means we're going to the left. All right. So again, mean 20, 4. All right. So be able to set this up. You don't have to draw your normal curve perfectly. Again, just make sure the highest point is in the middle and be able to do this. Most of the time, I will supply you with this on your homework. All right. So what gets into this? What does this set us up for? It's called the empirical rule. It's called the 68, 95, and 99.7 rule. Basically, guys, those represent probabilities. Those are percentages. Probability. Probability. This is all probability. So based on last class, when we dealt with probability calculating our own, this one takes into account large amounts of data, probability. So all this is probability. These represent percentages. All right. So additionally, every normal curve, regardless of the mean or standard deviation, conforms to this following rule. So it doesn't matter, you know, if my mean is 20 or 1,000 or -5. If it's a normal distribution, it's going to follow this rule pretty much exactly. It may be slightly off depending on the calculations and whatever, but majority of it, it's going to be right in this range. And this is why we call it the empirical rule, because it always works. It's the overriding rule. So what it says is that if you have data that falls within 1 standard deviation, all right, so we're looking at it between 1 standard deviation of each side of my mean. So we have mean here, down here, right? We have our mean here, dead center, and it says between this line and this line, 1 standard deviation of both sides. We have 68% of my data. 68% of the data will fall in between there. It doesn't matter if there's 100. If there's 100, there's 68 of them fall within this. Or if there's 10,000, then it would be 6,800 fall within these 2 standard deviations within them. So some will be in the mean, some will be outside, some will be right at the center. They will fall there. So 68% of my data. So what does that also tell us? Well, if the mean, guys, if you think about it, what does the mean do to this whole thing? Well, it splits it directly in half. This is the 50% mark. 50% mark. Now, most of the time, we're not going to represent it as 50%. We're going to represent it as 0.5. All right? It means 50% of the data is to my left. 50% of the data is to the right, right? So between there and there, it's 50%, 0.50. Between there and there, everything, 0.50. From the midpoint to the right, to the midpoint to the left, from the mean, there, everything's 50%. So we see in between here, 68%, which means if the mean splits that in half, that means that each of these little areas is 34. Just take 68 divided by 2. Each of these is 34%. This is going to be a point here, so keep that in mind. You need to write this down if you haven't already started. All right, then it says within the 2 standard deviations, so between 2 of them, we have 95%. So we get a bigger chunk. And you'll notice that most of the data, again, is concentrated towards the middle. So as we get further and further out, you see there's less and less. The normal curve kind of flattens out and gets smaller. It's because there's less and less data going out there. So between the first two, we have 68%. Between the second two, this line and this line, right, we have 95%. Which means that if the mean shuts that in half, that means between these two, half and 95 is 47.5. Well, that's great between the mean and the second standard deviation, but how much is in just this area over here? Well, if this part is 34, that to the right, to the left of it, if this part is 34 to the left, and we know this here to this here is 47.5, which means 47.5 from the mean to the second standard deviation, and the first part is 34. What's left of it? Well, 34 out of 47.5, you just subtract it, and you end up with 13.5%. And if it's 13.5 here, because it's symmetric, it's going to be 13.5% here. Now let's look at the top one, 99.7. So it's almost 100% of the data. So there's just a little bit on the outside, but between the top side, we have 99.7% of the data. So we're talking between here and here. We have 99.7%. So now a good thing again, let's think about it. How much data is it from the mean to out here? So again, it chops it in half. So half of 99.7 would be 49.85. Again, if you just took 99.7 and divided by 2, that's what you get. So again, if you want to use your calculator on this one, just for those who like using it, divided by 2, you get 49.85. Right. So 49.85. Well, again, we know between the first two, it's 47.5, 49.85. So the outer portion, even though it's the same width, because it has less data, it's getting smaller, there's only 2.35 out here. It's just 49.85 minus 47.5. So it's 2.35, which means, again, 2.35 on the out here. Now, what does that leave us on the outside? What does that leave us out here? How much is out here and how much is out here? Well, let's think about it. If 99.7% of the data is between those two marks, how much is left over? Well, it's 100 minus 99.7. And that's basically 0.3. And if you divide that by 2, it's 0.15. So each of this area outside of it is 0.15. Now, what I suggest you do is right now, pause the video, make sure you have all of this down. All the numbers in blue here, you want to have that, and you want to have the 99, 95, and 68. Because what we're going to do is we're going to use these numbers to help us answer questions. So again, if you need time to take it down, pause the video, write this down. All right, so here's an example of what's going to happen. This is the kind of question you're going to see on your homework and on your quiz coming up next class. An average light bulb manufactured by the Acme Corporation lasts 300 days with a standard deviation of 50 days. Assuming the bulb life is normally distributed, what is the probability that an Acme light bulb will last at most 350 days? So kind of a lot in there, but what we want to start out is we want to start with creating our normal curve. I've already drawn it in for you, and I gave you the middle line for the mu. All right, so for our mean, there's my mu. I'm going to write it down here. But we need to figure out based on the word problem here. So we're going to start out. So average light bulb manufactured by the corporation lasts 300 days. Well, guys, right there, that number 300, there's my mu. And then it tells me standard deviation is 50. So there is my little thing. So we can now take those numbers and we can put them on our graph. So 300. And then, of course, 1, 2, 3, 1, 2, 3. And so now we just put 350, 400, 450, 250, 200, 150. If you need to, you can always draw little barrier lines to help you out. And a good thing at this point would be also to kind of write in those percentages that we wrote down in the last one and go, all right, we know middle 68, so 34 and 34, and then we know we have 13 and a half, 2.35, and 0.15. And if you only memorize one side, that's fine because both sides are exactly the same. So if you just remember the right-hand side, it's easy to get the left. It's just reverse order going the other way. And by writing this down, it'll help us answer the question. So now let's actually look at the question. It says, what is the probability that an Acme light bulb will last at most 350 days? So we're looking for it lasts at most. That means it doesn't go over 350. So if we're looking for when is it less than 350? So based on what we're seeing at my 350 mark being right here, we're looking for everything to the left of that. Well, if we know that my mean is the 50% mark, then what is the first deviation? Well, it's 50% is everything to the left of the mean, and then I have this one block of 34. So it's 50 plus 34. So it's 50 plus 34, which gives me 84%. So I have an 84% chance, or 0.84. We would probably write more in decimal now. 0.84, but for these problems, we'll write 84%. The probability is that a light bulb will only last up to 350 days, 84% of the time. Which means, odds are you're going to have to replace a light bulb within 350 days. So it'll last almost a year. Could you have one that lasts more? Yeah, you have a 16% chance that it'll last longer than that. But for right now, 84% chance it'll last less than that. All right, let's look at another question. It says, what's the probability that an Acme light bulb will last between 200 and 350? All right, so now we're talking about 200 to 350. So we're talking those three. Well, we know the two in the middle here are 68 plus 13 and a half. So we're going to just do 68 plus 13 and a half. In this case, gives me 81.5. So it's 81.5%. And this is how quickly this can be done. Once you have your numbers down, all we're doing is going to add up or subtract parts. We're not even going to do much else than that. All right, let's look at the next one here. What is the probability that Acme light bulb will last longer than 400? So we're looking for greater than 400. So we're looking for 400 and out. Well, that's 2.35 plus 0.15, which is 2.5. So you have a 2.5% chance that it'll last longer than 400 days. So more than likely, it's never going to last that long. And then so what will be the probability that a light bulb lasts less than 150? So now we're looking for 150 and going down, which is just 0.15%. Not 15%, 0.15%. So if you get a light bulb that doesn't last 150 days, it's probably defective. You want to send it back, get your money back. That's what that tells me. Is that there's no matter what, should not have a probability this light bulb should last longer than that. That doesn't mean you leave it on 100 all the time, but in general normal use. Right. So it's 0.15%. So be careful with your decimals here. So when we're adding up, make sure you're writing it out correctly. Don't put 250%. Don't put 15%. It is 0.15. All right. So probability of the normal curve. All right, so we've been talking about this. If it is a normal curve, normal distribution, and we actually have a nice mean standard deviation, we can do the empirical rule. Normal distribution is continuous. Probability distribution has several implications. Total area, which is, again, what we were calculating, is up to 1. So if you went back and added all those numbers we got, it gives us 100% or 1. The probability of normal random variable x equals any particular value is 0. Basically, guys, if you just pick one value, the probability that you hit that value is negligible. And don't really worry about that. Probability that x is greater than a equals the area on the curve. So basically, guys, what we're doing is you're calculating the area under the normal distribution, which is what we were doing here when we were just looking for the blocks. These little blocks help us out. We're just adding the area under the curve. This is what the standard deviations do. They break it up into easily addable portions. All right. And this is basically how you figure it out. So greater than number is area under the curve plus infinity. But guys, we're going to do this. And if we can't do it through the standard normal, what we're going to do is we're going to use the calculator. And I'll show you how to do it here in a minute. All right. So yes, as I said, we're going to do this on the calculator. All right. So to find the probability under the normal curve, not using the empirical rule. So we're not using, I'm not giving you standard deviation. I'm not giving you the mean. That's very nice to use. Basically, what you'll see is the questions aren't very tailored to the empirical rule. What will happen is I won't give you a number, or I won't ask you a number that's going to be a standard deviation. Like I won't give you like, okay, we did 300 and 350. I'll give you something like 364. That's not a nice number on our curve, so we have to use the calculator to do it. All right, so what we're going to need to do this is we do need the mean and we need the standard deviation. That's guaranteed. We have to have those to do the probability. And then we're going to look for a lower bound and an upper bound. Now, lower bound, upper bound doesn't mean we're just going to take a small number and a big number. If we're looking between two numbers, we'll have a lower bound, upper bound. If I tell you we're going to be less than a number, our upper bound is established by that number, but the lower bound is going to be like some ridiculously number. Normally it would be infinity, but we can't write infinity on our calculator, so we're going to use a ridiculously low number. Same thing if we say we're looking above a number, we have the lower bound, and we'll be getting a big, big number. Again, ridiculous. All right. We got to have all four of these things. Now, I give you the key strokes here, right here. All right. To do this on a calculator, we are going to hit second vars number 2. It says normal CDF. Now, you'll see there's two normals, normal CDF and another normal. We want normal CDF, number 2. And then we're going to put in our lower bound, our upper bound, our mean and standard deviation, and then we're going to hit enter on paste. And this brings us back to the home screen, and we're just going to hit enter one more time. All right. And what I'll see on the calculator is this will produce this little thing that says normal CDF and then a bunch of numbers after it. Well, guys, it represents your lower bound, upper bound, mean, and standard deviation. And it computes a probability. It computes the probability between whatever the lower and upper bound is. All right. So here's a good example. Suppose scores on an IQ test are normally distributed. If the test has a mean of 100 and a standard deviation of 10, what is the probability of the person who takes the test will score between 90 and 110? Now, I do give nice numbers here because you could match the empirical rule, and that's what we're going to show. But let's do this on the calculator and show that the empirical rule actually does work. So we need our mean. So our mu here, and we have it as 100. Our standard deviation is 10. And then I'm going to put LB and UB for my lower bound and upper bound. So my lower bound is 90. My upper bound is 110. So now we're going to go back to our calculator. And to do this on our calculator, you hit second vars, and you'll see number 2, normal CDF. Hit enter. And it says lower bound. Well, my lower bound is 90. Upper is 110. Mu, which is my mean, is 100. And my standard deviation, 10, or sigma. And then we're going to hit paste, enter on paste, and then it brings up, again, like I just said. And then we hit enter. And we see that it is 0.682689. So, guys, when we're doing these probabilities, what I want you to do is with these decimals, write out 4. 1, 2, 3, 4. Not 2, 4 decimal places, because we turn it into percentages. You got to move the decimal 2. So we want 4. So my probability is equal to 0.68, and I lost it, sorry. 0.6827. 6.6827. There's my answer. 0.6827. So you see that basically, guys, remember, we said one standard deviation above and below the standard normal on an empirical rule was 68%. Voila. This basically follows the empirical. I told you to be slightly different based on calculations, but it follows that rule. 68% of my data is within one standard deviation of each side. All right, let's look at another one. What is the probability that the person who takes the test will score less than 85? So we're still going to use the same mean and standard deviation. Mean is 100. Standard deviation is 10. Now, less than 85. So my lower bound, my upper bound. Well, since we're less than 85, that's my upper bound. 85 will be my upper bound number. And then my lower bound number is going to be something ridiculous. Well, since we're using 100 standard deviation 10, I'm going to use like negative 1,000. It's so far away from what we're dealing with. And if you want to use like 10,000, 50,000, just depending. Now, if we're dealing with a big mean, big standard deviation, pick a bigger number. Pick like 100,000 down there. Way negative 100,000. Get way away from it. But in our case here, since we're doing hundreds and tens, we're going to be pretty much away from it. So again, second bars, normal CDF. My lower bound, I'm going to put negative 1,000. My upper bound is 85, and I'm not even going to have to change my mean or standard deviation because it's already in there. Paste, enter, and I get 0.0668. 0.0668. So my probability is equal to 0.0668, or 6.68%. So to score less than 85, only 6.68% of the population does it. That's pretty, pretty standard. If you're not that great, you'll notice 68% scores between 90 and 110. All right, let's look at this last one. What is the probability of a person who takes the test will score above 116? So again, my mean is not changing. My standard deviation is not changing. But my lower bound and upper bound changes this time. Now, we're doing above 116. So it gave me my lower bound is 116. What is my upper bound? Again, I'm going to choose 1,000. Again, we know realistically no one can have an IQ of 1,000. However, the calculator does not know that. So we just have to deal with it. So going back to my calculator. Second, VARs. Number 2. Lower bound now is 116, whereas my upper bound is now going to be 1,000. And I'm putting 10,000. I'm just going to put 1,000. I'm going to delete that. Go down, paste. Again, I don't want to change mean, standard deviation. Paste again. And I got 0.054, and I'm going to round that to 8. 0.0548. Probability is 0.0548. So only 5.5% roughly of the population scores above a 116. So you're in good company if you got an IQ above 116, based on this data. Doesn't mean in real life that's the way it falls, but this is just a general take. And IQs are easy to understand. All right. Hopefully, again, if you do not understand this, rewind, go back and look at it again. All right. So now, given that this was finding probability, what happens if we know the probability, but we want to find certain other things? They give us probability, but ask for the number that it represents. So now we're going to say, all right, given a probability, what number would this represent in the data? All right, so we're going to kind of go working backwards. Now, again, the calculator will do this for us. We're going to use what's called inverse normal or inverse norm, and that's what you'll see on your calculator, inverse norm. So that's why it's highlighted purple here. Inverse norm computes the value for which the probability falls at or below. In other words, it computes the 100%. Basically, it's computing the percentile. So think about it, guys. If you were in the 75th percentile in terms of height, we could actually calculate the height you should be at, knowing the mean and standard deviation of the population they're calculating. I could give you the exact height you are. Without you telling me. Just if you told me the percentage, the mean, and standard deviation. All right. So, or case, if using 0.25 for P will give you the number that represents the 25th percentile. All right. So again, I give you the calculator keys right here. We're going to do second VARs, and then what you'll notice on is number 3 on that list says inverse norm. Now, so we're going to be using numbers 2 and 3, just depending on what the problem is. All right. We're going to fill in the area as a percentage as a decimal. That's the key right there. It has to be in decimal form. If you put it in as a percentage, like 38%, it's going to give you an error because you can't take in an area or a probability greater than 1. So it has to be less than 1. So what you would do is you go, all right, convert it decimal form, 0.38, and it'll work. All right. All right, we're going to plug in the mean, standard deviation as we did beforehand, hit enter, let it go. All right, so good example here. What is the 78th percentile? So we couldn't figure this out based on using the standard normal because we get 68%, blah, blah, blah. We can figure out those percentages based on where they're at, but we can't figure out ones in between. Again, the calculator would do this. 78th percentile, given the mean is 100, standard deviation 10. So we're looking, basically going for our IQ here. We know my probability is 0.78. We know my mean or mu is 100, and we know the standard deviation is 10. So going back to the calculator again. Second, VARs. Number 3, inverse norm area, we're going to put in 0.78. Mean is 100. Standard deviation 10. Paste and calculate it. And you see that the 78th percentile with a mean of 100, standard deviation 10 is 107.72. Now this one you can round to 2 decimals because we're taking an actual number. 107.72. And that's my answer. So someone with 107.72 IQ would be in the 78th percentile. All right, so let's look at the next example. Bill claims that he can do more push-ups than 90% of the boys in the school. Last year, the average boy did 50 push-ups with a standard deviation of 10 push-ups. Assume push-up performance is normally distributed. How many push-ups would Bill have to do to beat the 90% of other boys? So it's telling us, all right, my probability at this point is 0.90. We're looking for that mark. All right. We know the mean is 50, and we know the standard deviation is 10. So that's what we're going to plug into our calculator. All right. So on the calculator, do the second VARs. Number 3, we're going to plug in 0.90. We're going to 0.9 is fine. Mean 50, standard deviation is still 10. I'm going to keep that there. Paste, enter, and we see it's 62.81. So 62.8, basically 0.8, right? 81, 82, 82. Now, can you do 62.82 push-ups? No, because we don't count non-push-ups. So what does he have to do? He has to do roughly, in this case, 63. Just because we're actually for an actual number of push-ups that physically he has to do, 63. The value would be 62.82, but the actual number he needs to do is 63. If he does 63, he will be above 90%. If he does less than 63 or 62, he doesn't do more than 90. He's still in the 89th percentile. So be careful. In this case, to do better than 90%, he needs to do 63. So he has to do 63. All right. All right. So again, at this point, if you need to, go back, rewatch this, learn your keystrokes. All right. Good video. Next class, remember you have a quiz, and then we're starting to review for the final. So if you have any questions, please come see me, and